A very good afternoon to everyone present here. I'd like to welcome all of you to this final installment of the workshop series for ArcGIS Platform webinars. So the topic for today's webinar is spatial analytics. Uh, the allocated speakers for today's session were supposed to be Mr. Karthike Hadia and me, but Karthike for some reason is unavailable today. So we'll move on with further itself. To start with, I'll lead you through the brief agenda for the day. So the agenda for today is going to be, we're going to talk about the basics of spatial analytics and what spatial analytics is all about and how it is actually applicable in the ArcGIS environment. We will also then be talking about the types of spatial data, which include vector data and raster data. And for each individual data types, we will also be talking about what that data is, and additionally, the type of analysis that can be done on vector and raster data, respectively, in the ArcGIS environment. Now, before I start, I'd actually like to share a quick story about how GIS and spatial analytics uh, helped in containing cholera outbreak in London in 1854. Just so that we can avoid any disturbances, we'd welcome all queries once the session is over, and I'm sure we'd like to take those up. Right. So this cholera outbreak that happened in London in 1854, a personnel created a a map based on the survey data, which actually helped this person identify a clear pattern which no one had noticed until then, and then ultimately determine the source of the outbreak. So, although this unnamed personnel is not really a cartographer, he is widely viewed as the pioneer in disease mapping for the study of epidemiology. Now, that is basically what helps. That is how rather spatial data analytics can be utilized. It's just a very basic example, but what started back in 1854 has evolved into what we're going to talk about today. So, a geographic information system, a GIS, it basically allows you to compare and analyze geographic data and find patterns. So while the term GIS did not actually exist back in 1854, this map of the cholera deaths allowed this personnel to ask questions and solve problems just like we do with GIS today. Now, what exactly is spatial analysis? Now, spatial analysis, based upon the definition, is the process of examining the locations by identifying patterns or determining trends, attributes, and relationships of features in spatial data through overlay and other analytical techniques to address a question or gain useful knowledge. So when we're talking about spatial analytics, what we're exactly saying is that based upon raw data which is being input, we are actually able to identify certain trends, certain patterns in the data itself, which can actually help us solve the end requirement, or rather uh, build a solution for a problem which may not actually be tackleable when we're talking in the terms of a raw data itself. Now, uh, what is the general workflow for performing an analysis? The first question that comes in is asking the relevant question, which means if we are talking about the cholera example, which I gave in the beginning, so the question in that case would be is where is the most amount of population which is highly affected, or which part of the population is more highly affected than the other. And then the second step that follows up after this is exploring and preparing data. So which means getting the relevant data. And in this case of the cholera example, it would be getting the case population data, the water lines, water pumps, or residential house data, as well as the number of people involved. Basically, again, the population data itself. Now, when we have actually brought up a query towards a particular requirement, we have the corresponding data also required. The next step that follows in is actually analyzing the model. So when we're talking about analyzing the model, we're actually talking about analyzing the data for any patterns, trends, or relationships. So in this case, in the case of the cholera again, there were patterns and relationships which were found between the cholera affected population and water pumps and lines. So which basically helped uh, this unnamed user identify that back in 1854, he managed to identify that any population which was located close to water pipelines or was located close to pumps based upon their residential data also was the most highly affected. So this falls in the part of interpreting the test results. So once he's actually created or analyzed the model, he has interpreted the test result, which is the fourth step, right? Comes in the process of actually cross-verifying the output. So once you have actually obtained an interpretation, you have a final output that you're looking at. You can either repeat or you can modify your model in such a way so that you can improve the accuracy of the analysis. You can maybe try and find some other factors, or in case you feel the procedure that was followed to actually identify the corresponding outcome wasn't accurate, in this case such modifications can be made to accordingly work to make the result even more positive. Now once the same is done, the final two steps are related more with respect to administration, wherein we actually take the entire set of analysis that we've done and we present these results to the concerned authorities. So in the case of the cholera outbreak, we could talk about presenting the authority, presenting the outcomes to the corresponding sanitation authority in London, or maybe something like that. And then accordingly, in the final step, that corresponding administrative body or that authority takes the final decision on how to actually tackle that. Right. So in this case, when we're talking about the make decision scenario, what that particular authority, like if you take another example, it could be the example of the COVID outbreak and how India responded to it, what issues were identified, accordingly the spatial analysis that was done to identify the areas which had a higher level of cases. Accordingly, the analysis was done, the results were interpreted, actions were taken accordingly. So that is the entire workflow for an analysis here. Now, before we actually go further and start talking about the data itself, there are certain basics also which we need to understand, which for starters is spatial reference. So what is a spatial reference? A spatial reference describes where features are located on the globe itself, or in the world, where exactly a particular feature is located when we're corresponding that data onto the map itself. So there are basically two types of geographic coordinate. There are two types of coordinate systems that are popularly known, which is the geographic coordinate system and the PCS, which is the projected coordinate system. Now, a geographic coordinate system uses a three-dimensional ellipsoidal model of the Earth's surface to define locations using degrees of latitude and longitude. And a projected coordinate system uses information from geographic coordinate system and translates it to a flat surface. So each projection will actually preserve a certain aspect of the data. When we're actually projecting this GCS into PCS, we can maybe preserve certain aspects like area or direction, shape, distance, and so on, at the expense of other aspects. So that is a key point there. Now, it is important to choose projections carefully based upon what aspects of your map are the most important. So generally, a PCS system usually defines locations using X and Y coordinates in feet or meters, and so on. So if you want to perform an analysis on maybe a large area, generally a GCS is more suitable in comparison to when we're actually analyzing a smaller area, in which case a PCS works more efficiently. Now, this diagram right here showcases how we're actually projecting the geographic coordinate system onto a 2D map using the 2D Cartesian coordinates, and we're converting that 3D globe surface onto projecting it onto a map plane. So accordingly, as we discussed, there will be certain like we will be able to preserve certain aspects, and then there'll be a loss of certain aspects in terms of either area or direction and so on. And the factors that actually play a part here are the geographic coordinates, which are the latitude and the longitude angles. Now, moving further, we need to understand there are certain factors like scaling also involved when we're projecting the data from a 3D surface to a 2D surface, which means we're actually representing the real world graphically onto a printed map. So this is done using map scaling. And map scale specifies the amount of reduction between the real world and its graphic representation. It is usually expressed as a ratio. For example, maybe 1 is to 20,000 or 1 is to 2 lakhs, which in actual linear units is equivalent to approximately 1 millimeter on the map can be equal to nearly 20 meters on the scale, on the ground. Now, a map scale is also relevant when we're selecting a type of a geometry to use and scale and the scale of an analysis. For example, working at the country level or a city level, and so on. So when a map scale is too small, that features are too small to be represented as polygons or as polygons, then maybe points can be used. So, for example, if you're talking about viewing city boundaries on a global scale, uh, the polygons on a global scale are so small that they cannot be represented accurately as polygons, in which case we can display them as points. So that is how map scale comes into play. Now, as visible on the screen right here, on a global scale, when we're trying to represent uh, cities, we can only represent them in the form of points. However, on a much larger scale, we can represent it with a greater ratio value accordingly, and then display those points in the form of polygons. Now, the display scale of a map is actually the scale at which the map looks the most accurate. So when we're talking about uh, a particular map which is on a local level, when we're trying to maybe display certain blocks, so then the corresponding scale which is utilized to display those set of blocks accurately within the extent of the map is our display scale. Now the amount of detail on the map must never be overwhelmed as such, which means that in case the map becomes too crowded, then there'll be uh, then possibly there'll be areas of the detail which will be merged into big black blobs as such when we're talking about printing the maps. And most of the text on the map will be too small to read also. So identifying the correct scale for display is really important. Now, these small basic concepts that we have here play a major role in understanding how spatial data is analyzed, how it is used, and finally, how it is represented to give the corresponding output. We can now come down to the type of spatial data that we mostly work with. We'll first start with vector data. So what exactly is vector data? Vector data or vector graphics, as popularly known, are comprised of vertices and paths. So vertices are the points with corresponding latitudes and longitudes. And there are three basic types of vector data which are mostly used, which are points, lines, and polygons. So cartographers use these symbols to represent real world features in maps. They often have to decide based upon the level of detail on the map, as discussed in the map scale and display scale earlier. Within the vector data, points can be defined in the terms of x and y coordinates, which is the longitude and the latitude with a specific spatial reference. So just the latitude and longitude is not important. Obviously, the spatial reference that we were talking about also plays a major part. And as far as representation of certain features onto the map is concerned, points can be used for representing certain events, locations of interest, data points in terms of when we're talking about demographic data or certain other details, for example, survey points. And then in case we're talking about a more small scale map, then if we have when the features are actually too small to be represented using polygons, points are most successfully used as discussed earlier. The other one is polylines. So vector lines which basically connect each vertex with paths are polylines. So when you're connecting in a very simple language, when we're connecting the dots in a set order, it becomes a vector line with each particular dot representing a vertex. Now, when we're talking about polygons, or rather, I'm sorry, these polylines actually help you represent linear features which have a certain linear nature. So, for example, rivers or roads, pipelines are certain most popular examples of vector lines. Polygons, on the other hand, are basically formed when we join a set of vertices in a particular order and close it, which means that we are following or referencing a specific order of the points itself, but we are connecting the first and last point to close that particular vector flow to form a closed structure, and that formulates our polygons. So polygons most popularly are used by cartographers when they want to represent boundaries. For example, they have an area or a building footprint which has a square footage, and agriculture fields, for example, which have acreage. So accordingly, all of these are certain examples. There are other types of geometries also which play a major part within spatial data. That includes multi-part geometry. So a multi-part feature is basically composed of multiple shapes grouped into a single feature, which has only one record in the feature class table. So in case we're talking about a multi-part line feature, what we're actually talking about is individual lines have all been grouped together to form a single uh, feature. And each of these part is called a path, P-A-T-H, a path. Now, in terms of a multi-part polygon feature, uh, similarly, each of these polygons are referred to as rings. So both of these paths and rings are further comprised of segments, and accordingly, line and polygon features can support multi-part features automatically, which means that it is not a specific type of data type, but point feature classes cannot. So in case we want to store point feature classes, then we have to store them separately as a new feature class type. And accordingly, the data type of that feature class is multi-point features. Now, this is about the data that we're talking about.
Can you give a real-time example of this?
A real-time example of a
This
multi-part
line and
multi-part
multiple
feature.
polygon, yeah.
So generally, when we're talking about a multi-part feature, in case we're talking about multi-point, survey points are most popularly used as multi-points, because often at times certain locations within the surveys have certain demographic data which is being represented, and we cannot actually aggregate the entire set of data in case we're taking it within a closed section. So we can aggregate that entire set of data to give a certain value, and that can be stored as a multi-point. That's one example. When we're talking about polylines or polyline, often at times within large scale maps, if we're representing the roads rather than as a polygon, as a polyline, wherein we want to show the sides of the line itself, that can be used as sides of the road itself in two individual features, then the best way to represent that would be a multi-part polyline. And when we're talking about a multi-part polygon, the best case scenario can be in the cases of agricultural land, wherein you may have certain scenario that there is one particular land which may be separated by a ravine or a particular stream. But in case the owner of the land is the same, then rather than trying to represent that land as two different parcels, it can be represented as two different features bound together in a particular multi-part polygon, wherein that river or ravine can be represented by a separate feature itself, like a polyline feature or a multi-polyline based upon the requirement. So these are certain examples as to where multi-part geometry plays an important role. Now, moving forward, when we're actually talking about analyzing vector data, there are certain spatial queries that play a very important role. So selecting points using line, when we're talking about that. So within this, we have certain key factors in case we want to select certain points based upon lines. We have intersect, wherein if the input feature intersects uh, the particular line feature, then that means that it falls on the selecting line itself, and hence it is classified as an intersect. The within actually is used for boundary of points. So a boundary of the points lies within the boundary of the line. Now, a boundary of the point will be the point itself, and the boundary of the line will actually be the two endpoints of the line. So in case the particular point lies within the endpoints of the line, then in that case, it is considered as within. Completely within is when the boundaries do not intersect, which means that the point lies on the line itself, but within the two endpoints and cannot intersect with the endpoints. Uh, for points within Clementini is the same as within, and have their center and works under the case that this particular feature, the centroid of the particular feature, which means the point itself, falls on the line. Boundary touches will be the case reverse of completely within, wherein the point actually falls on one of the endpoints of the particular line feature. If you are trying to select a point using a polygon, then in that case we have certain queries also which can be fired. I'll request all the users to keep their mic on mute, please. Within this, the most popularly used is intersect. And if the input point feature intersects, that means it falls in the selecting polygon feature itself, then intersect can be used. Similarly, within can be used when the point lies within the boundary of the polygon. Completely within falls under the scenario that the point lies within the boundary of the polygon, but does not actually intersect with the boundary itself. Within Clementini, again, for this case, is the same as within. Have the center in works under the case that the center of the point actually falls inside the polygon boundary. And boundary touches will be valid under the case that the point actually lies on the boundary of the polygon, which means in case it lies inside the boundary touches spatial query cannot be held as valid. The next one that we have is selecting line using line. Now, within this, these spatial queries that fall which are most popularly used are intersect, which again is in case the input line feature intersects, that means falls on the selecting line feature, it is classified as true. Contains works that in case the input feature overlaps the selecting feature completely, which means that in this case, if we're looking at our uh, options G and H, the input feature, which is the green one in G, is actually the input feature, and it actually contains the selecting feature, which is in gray. So uh, it falls within the boundary, in which case this becomes true. Similarly, completely contains this in case it overlaps completely end to end, then that is held valid. Contains Clementini for lines is the same as contains. Within works in case the endpoints of the selecting feature the input feature lie within the length of the selecting line, which means if you look at the example, if you look at F and H, so we can see that the green line, which is our input line, lies within the boundary of the selecting feature, the gray feature. Hence, that is valid. Similarly, completely within will be valid in case the line falls onto the selecting line itself, as long as it does not touch its endpoints. And within Clementini for lines is the same as within. Are identical works under the case that the two lines are absolutely identical and overlap perfectly. Excuse me. Now, in case we're trying to select lines using polygon, we generally work with the following categories. The first one being intersect, wherein if the input line feature intersects, which means it falls on the selecting polygon, it is classified as intersect. Within works under the case wherein the endpoint of the line lies within the selecting polygon and may intersect the boundary, but definitely does not extend beyond it. Similarly, completely within falls under the case that while the feature lies, like the entire feature lies within the polygon boundary itself and must not touch the boundary. Within Clementini, in this case, again, is the same as within, with just a small variation that it does not lie completely on the boundary of the selecting feature, which means in case the line lies completely on the boundary of the selecting feature, then in that case, that cannot be considered as a valid option as shown in the diagram in section O. Now, share a line segment is one wherein the input selecting line shares a line segment with the polygon boundary itself. And crossed by the outline of works under the case wherein the boundary of the polygon intersects the line, but not its endpoint, and has their center in works under the case wherein the center or the midpoint of the line falls within the polygon. Right. The final spatial query that is important, set of spatial query which is important to understand is selecting polygons using polygons. Now, within this is actually the largest set of query options that we have available. We have intersect, wherein in case the input polygon falls within, which basically intersects or overlaps the selecting polygon, then it is classified as an intersect. Within contains works under the case where the input polygon feature overlaps the selecting polygon feature completely. Completely contains is valid under the condition that the input selecting feature overlaps the input feature actually overlaps the selecting feature completely as long as it does not touch its boundary. Then contains Clementini works as the same condition as contains here, and within is valid under the case that the boundary of the polygon lies within the boundary of the selecting polygon. Similarly, for completely within, the input polygon should lie within the boundary of the selecting polygon, but not touch the polygon boundary itself. Similarly, for within Clementini is the same as within, and then are identical to. In case the two polygons are absolutely identical, then which means they overlap perfectly, then that condition is held as valid. Boundary touches is valid when the polygons do not overlap, but simply their boundary features touch each other. And share a line segment means that a particular segment of the input selecting polygon boundary actually overlaps the boundary segment of this selecting feature. Crossed by the outline of works when in the boundary of one polygon intersects the input polygon, but there is not a complete overlap. And has their center in is valid when in the case the centroid of the input polygon falls within the selecting polygon. Now, the reason we actually brought up these spatial queries is because the essence of entire spatial analysis is dependent upon the spatial query when we're talking about vector analysis, because understanding how these properties help correlate features, which means points with lines, points with polygons, and so on, actually helps us determine the final output and cater to the end requirement. Moving on, we have vector analysis. So uh, now that we've understood what the basic spatial queries are, what or how spatial analysis can be done, we now need to understand how vector analysis can actually be performed. So we're going to talk about certain operations that can be done with vector data. And ArcGIS is actually excellent for querying your database based on spatial relationships defined in the software, for instance, on the basis of proximity, containment, and intersection. Uh, in essence, spatial querying is actually similar to finding features that are located in a certain way relative to other features. So as we were talking about earlier, these query objects within the same layers or between different layers with different geography is possible, and that actually helps us analyze the vector data properly. Now, there are different types of analysis that we'll be talking about. So to start with, we have single layer geoprocessing options or single layer analysis in vectors, which can be best represented by the case of buffer, dissolve, and merge. Now, the buffer actually helps create buffer polygons around the input feature at a specified distance. So in case we have an input point and we give the threshold value for the buffer around 50 meters, then the buffer geoprocessing operation actually helps us create a boundary of 50 meters beyond the point of the polygon with, sorry, the point where the point actually acts the centroid of that buffer formed. Similarly, for lines, accordingly, a threshold value can be given and the buffers can be formulated. And similarly for polygons also. So within proximity analysis, buffer plays a very important role. Another one that we have is dissolve. So dissolve, as you can see in the diagram also represented here, it helps us aggregate features based upon a certain attribute. So in case there are certain features which share a specific boundary and they have a definite attribute also which is being represented here in this case, then accordingly that particular set of features can be combined to form a single output itself, and that is dissolved. The third one that we have, which is very popularly used, is merge. So merge actually combines multiple input data sets into a single new output data set. So you may have, for example, if I was to explain where merge works best, is in case we're talking about a sheet-based distribution of data, wherein each geospatial sheet represents 1 kilometer by 1 kilometer area of data, and accordingly you want to analyze the total area of, let's say, which is covered by 4 different sheets. So rather than having to analyze it individually, running a merge on the entire data set can give us a combined output layer to work with, which can be utilized for further analysis. Now, within vector analysis, multi-geoprocessing or overlay options are also very important to understand. So as represented in the diagrams on the right, these geoprocessing overlay options actually help in identifying a lot of spatial properties. So for example, we have 2 different data sets that we're working with. The union overlay method helps us actually identify a combination of the two. The union overlay method employs, for those personnel who understand logical operators, it actually employs the simple OR operator, which means a union can be used in the case 2 polygons are used as input layers, and it will give us all the features. It will basically preserve all feature attributes and the information and the spatial extent, and give us a combination of the 2 polygons as output. Alternatively, the intersection overlay method basically employs the AND operator, which means that it acts as an intersection and requires a polygon overlay, uh, but it can actually accept lines and polygon inputs also both. So the output layer covers the spatial extent of the overlay of the 2 features that are being provided as input. and it contains features and attributes from both the inputs. So although it is combining the input attributes, only the section which is intersecting or overlaying for the two features is provided as output. The symmetrical difference is actually the opposite of AND itself, and works on the XOR operator, which means exclusive operations in terms of a combination of the two without their intersection. So a union minus the intersection will give us the symmetrical difference. This method requires both the input layers to be polygons and only works under that condition. And the output polygon layer produced by the symmetrical difference method represents the area common to only one of the feature datasets. The identity overlay method creates an output layer with the spatial extent of the input, but it includes attribute information from the overlay, which means that the input layers can be all points, lines, and polygons. However, the identity layer, which means the layer for which the entire attribute information is being provided, must always be a polygon dataset. The clip or geoprocessing operation is used to extract the features from an input point, line, or polygon layer that falls within the spatial extent of the clip layer. The erase works as a reverse of the clip operation itself, wherein it actually removes features uh, from within the area which is overlaying. So it preserves only those areas which are actually outside the extent of the analogous erase layer, which is being provided as input. And while the input layer can be a point line or a polygon dataset in this case, the erase layer must always be a polygon dataset. The split geoprocessing operation is used to divide an input layer into two or more layers based on a split layer. So, as you can see in the representation, we may have an input layer and we may have a grid layer or a split layer that we're working with. So, it actually helps in dividing this data set into individual data sets based upon the split layer boundary. This again, as we were discussing earlier, wherein the general procedure allows us to combine our features, which with the merge tool. Split actually helps us distribute it along the same rule itself. Now, if you to give you a more prevalent example of how analysis can be done using vector, one of the most popular analysis is hotspot analysis. So hotspot analysis is actually in a very simple way the analysis which is used to identify the areas of the maximum frequency corresponding to the areas of minimum frequency. So in case you have point data with respect to representing areas of higher population, or rather we have demographic data which represents the population across US, for instance. So we can actually perform hotspot analysis, and this may not necessarily be in points only, but using that we can identify which areas have the highest population, which will be represented by a much darker shade of red in correspondence to the areas which are of a relatively lower population, which can be represented in darker shades of blue, the general symbology which is used for representation of hotspot analysis. So the image on this on the left side of your screens is actually a classified image for social media usage in different US counties within each individual state of the United States. And on the right, it is actually the analyze out. So we can get into the analysis procedure later on. But to represent what the input and the output looks like, the right image on the right contains these red colored areas which indicate that they have statistically significant clusters of high social media usage, and can be represented to as the hotspots or the so as to represent the popularity gain. On in comparison to that, the blue sections, the sections which are blue in color, actually indicate areas which have a statistically significant cluster of low social media usage. So they can be referred to as cold spots. Now, the varying shades of these colors indicate how confident the analyzer or the analyst can actually be to identify which areas are more popular or more useful with respect to the analysis that is being performed here. So these varying shades of the colors from, let's say, high to low can be used to find the result of random chance and finally builds meaningful spatial patterns. Now, besides these popular analysis types that we have just discussed, there are certain other spatial analysis also, which are available within the entire spatial analysis toolbox. Now, the process is classified under proximity. So within proximity, we're talking about viewing and analyzing data based upon the distance between features. So in case we have uh, multiple features which are being used as input, then to correlate based upon the distance, we will use proximity, wherein multiple tools like the distance tool or the proximity tool set can accordingly be used. Furthermore, we have the overlay, which we just discussed earlier. So the overlay tool set and local tool set and zonal tool set can all be utilized for this to identify overlapping features. Network is dependent upon the network analysis, which may generally relate to a specific type of a network that we're working with. And then we have other spatial analysis categorizations of statistical, 3D, and temporal, with statistical dependent upon statistical data being used to analyze the output. 3D is used to view and analyze data in a 3D context, which means spatial analysis in a 3D context is done under this scenario. And temporal data is when we're talking about multidimensional tools working to identify patterns over time. So this basically was a brief insight into how vector analysis can be used within ArcGIS. Let me just lead you into a small demo for vector analysis. Right. So in this demo, we'll actually be talking about using the ArcGIS Pro platform to predict the PM 2.5 and find cities farthest to monitoring sites in California. So we have this range of data sets where we are actually representing the yearly average and maximum values and average AQI as just represented within various locations. We also have available the demographic data for populous areas of California. And we have the county level boundaries for California also available accordingly. Now let's look at some of the geoprocessing tools which we have available in action, which we discussed during the presentation itself. Let's say we want to actually distribute California into northern and southern Californian regions based upon the attributes in the California data layer. As represented, we'll go to the title bar, and within the title bar, we'll click on the Analysis tab and Access Tools. From the tools, we will be able to open the geoprocessing pane on the right, wherein we can search for our dissolve tool. Within the dissolve tool, we can take the California layer as an input and dissolve fields such as state part. Rest we can leave to default, and you can provide any field in case we need to calculate any statistics for the dissolved features. It helps us see that the features are then merged within the output that is just visible. Let me just go back there. The dissolved output, which was just, I'm sorry, right. The dissolved output actually helps us identify two different sections which have been classified based upon the state part attribute, which is available at the bottom of your screen. Now, let's go further to the prediction part. As we can see that the PM 2.5 monitoring stations or the monitoring data points are not distributed all over California. We have certain concentrated points, some are not. So, in order to predict the PM 2.5 values for other California regions, we need to interpolate the results. Now, for this, we will be using the empirical Bayesian kriging to interpolate the values. In the geoprocessing pane, search for empirical Bayesian kriging and open the tool. The annual take annual PM 2.5 as input features, Z value field as the field value which we want to predict. We will take a yearly average in this case, provide the name for the output raster, and rest we can leave to default. Now we need to set the processing extent of the tool the same as California, as the points are not distributed everywhere around California. So we can then access the environment tabs in the tool and set the processing extent as that of California using the processing extent pane, and then finally run the tool itself. Now, for further modifications that you may want to do to actually generate while the tool is actually running, we can bring that up. You can to make more modifications, you can explore the geostatistical wizard within the analysis pane. On the top, as you can see, we have the geostatistical wizard also available, which is the fourth from the right under the workflows ribbon. That can be used for further detailed analysis accordingly. Now, one thing that we need to remember here is that this tool does not provide totally accurate predictions. So many parameters such as data distribution, model parameters needs to be taken into consideration. And what we're representing here is just for demonstration purposes. Now we have the raster of the predicted values. We can change the symbology as needed for better visualization. But first, we only need it for California. So rather than changing the symbology, let's clip the raster to operate only till the extent of the boundary of California. For that, we'll open the clip raster tool in the geoprocessing pane. We'll take the predicted raster as the input raster, and the output can be set as extent for the California layer, which we have available. Check the input features for clipping geometry, and then run the tool. Now we have the raster clipped as output once the tool is executed. This output gives you the required clipped raster itself, but we can change the symbology as per the distribution for a better visualization. So here we can first change the color scheme to prediction, which is used for generally prediction color ramp, and we'll use the standard deviation as stretch type for smooth surface. So you can check for values by clicking on the map. So in case you want to identify the areas which have a relatively low density, then accordingly we can click on the map to identify the corresponding values. For a larger section using the boundary, we can work with the corresponding raster which is required. Click on the area and identify the predicted value. So that will give us an idea of the minimum and maximum available. That can also be done using the minima and maxima available within the raster itself. So Accordingly, when we've set the corresponding corresponding symbology, that will give us the predicted PM 2.5 for this. Now, let's say we need to find the mean of the PM 2.5 values for each county in California for some further analysis. We can even use zonal statistics. So in the geoprocessing pane, you can open the zonal statistics tool, take the California input raster or the feature zone data. And for zone field, take the name LSA D10 field, which is available in the data set itself, which contains the county names itself. And for input value raster, take the clipped predicted raster, which we had initially generated. And for mean, we'll keep the statistic type as mean accordingly. Now the rest can be kept as default in this case, and we'll execute the tool. In the output raster that has just been generated, we have the PM 2.5 values for each individual boundary. So earlier it was it was classified across the region of California. Now we have further brought it down to each county level. Now, next we want to find out how close the nearest monitoring station site is to each populated place. So for this, we can use the near table or the near analysis tool. So search for the generate near table tool in the geoprocessing pane. Once you've accessed it, provide the input features as a places layer, which will be the annual PM 2.5 for the near features, and then set the output table search radius and accordingly run the tool. By keeping all the other parameters on default. Now, for running all the features, we must identify that there is a scenario wherein certain features are at a time selected, in which case only the corresponding value of those particular as visible, we've only received it for the selected feature. So we can clear this and then rerun the tool again to identify the near table for the entire section itself. Now, the first value now shows the ID basically or the feature that is furthest from the PM 2.5 monitoring sites. So we can check this feature by going to the places table using the select by attributes option and click on new expression and take the object in the first drop down and equals to the second drop down, which is 450 in this case, in the third drop down then, and click on apply. Going to the selected records and right-clicking on the record and clicking on zoom to feature can help us identify where that feature is exactly located. And that we can use for planning next monitoring sites accordingly further. Now, this brings us to the completion of vector analysis. Furthermore, we will now dive into raster analysis. But before we do that, do we have any other queries?
Yeah, Sarthak, we have a question from Vaibhav. It's in the chat.
Just
so why can't we take simple IDW interpolation? If you want, Vaibhav, feel free to unmute yourself. And if maybe we can take 5 minutes or so because we had a few hands up. So Vaibhav, if you want to go first, unmute yourself. Or Sarthak, if you've got the question, you can take it up.
Yes, I have the question in front of me. So, Mr. Vaibhav, we can definitely use simple IDW interpolation, and that definitely gives us that is actually a much simpler workflow. The only reason we have used this workflow here is for the purpose of representation of a greater set of analysis tools. But definitely, if we get into the nitty-gritties of which workflow is more efficient and can be used more accurately, then I will definitely agree with you that we should be referring to IDW interpolation. We do have some hands up also from Mr. Raj Pandey. Mr. Raj Pandey, I think you've also mentioned in the chat that you need access to the PPT. So I must apologize for that. We cannot share the PPT with you. but we can definitely share the content accordingly. And in case you have any queries, we can definitely take that up as well. Uh, do we have any other queries also?
Hello, myself Aditya. Yes, I do have one. And one suggestion. Maybe I can start with the suggestion. It would be nice to have a slide number, which I didn't find. Maybe I missed. And another thing which I wanted to know was, can you please elaborate more on identical and clip? Because on like based on visualization, it seemed to me like they are a bit similar. So yeah, it would be very nice to have some more light on this identical thing. Thanks a lot, Sarthak.
Uh, can you please let me know, sir? I mean, we have the clip option
This
available
one,
here.
just previous slide. Yeah, this one.
Yeah, this one
Vector
right here.
analysis.
Yes.
Yeah, exactly. Identity,
Yeah.
sorry. Identity. Yeah.
Identity and clip. Okay. All right. That is where I got a little confused. As in, like, identical is a part of the spatial query system. So
Yeah.
yes, the identity overlay operation. When we're actually talking about the identity overlay operation, sir, what we are doing here is that it is basically, you know, used to create an output layer. Wherein let's assume you have the first layer, which is the rectangular layer, is our input layer, right? But we also need the particular attributes of another layer which may overlay it. In this case, we'll assume the second layer is the overlay layer. So the identity layer is the first one. The second one is the overlay layer. What happens is that when we run the identity operation, the spatial extent remains the same as that of the identity layer. However, only the section of the overlay layer which actually falls on top of the identity layer, uh, those respective attributes are added to the corresponding identity layer. So in case we have layer A and layer B, so only the section of layer B which falls on top of layer A will then be added to uh, layer A itself. So in a way, it is actually those attributes are appended to layer A, and the overall spatial boundary, however, remains the same. Does that clarify your query?
Yeah.
Yeah,
And is it
right.
possible, like I have one query, like question maybe after the end of the presentation, is it possible to address that query after the presentation? It's
Sure,
related
sir.
to, sorry?
I guess we can take up raster analysis since we have limited time. But definitely, once raster analysis is covered, I'd love to take your query up.
Okay, thanks a lot. Thanks a lot.
Right.
Yeah,
You're
we can
welcome.
do it like this.
Right. So we'll then move on to raster analysis, and we can take up the remaining queries once we've covered this entire session. Now, to start with, what exactly is a raster analysis? And raster analysis is actually dependent upon raster data. So when we're talking, excuse me, when we're talking about raster data, we're talking about pixels being used as the key element for formulating the data set itself. So these pixels are often referred to as grid cells also, and they are usually regularly spaced and in a square shape. But they need not necessarily be. So generally, they exist in a square, but they need not necessarily be in that form. Now, rasters often look pixelated because each pixel has its own individual value or its own individual class. Thematic data, which is also known as discrete data, is used to represent features which, such as land use or soil data, for instance. Similarly, continuous data is a more smooth data when we're using rasters and can be used for temperature or elevation and satellite images accordingly. And another example of raster data are the pictures, which include scanned maps or drawings, which are used for, or even building photographs, in fact. Now, there are two main raster types which we need to understand, which which are used popularly. So the first one is the single band raster. So these rasters which have a single band or a single layer actually represent a single characteristic. So this characteristic of data that they're representing is actually in the form of a single matrix of cell values, and the raster with in comparison to the raster with the multiple band, it contains multiple spatially coincident matrices of cell values, each represented by an individual layer. So an example of a simple single band raster data set will be a digital elevation model, wherein only elevation is represented accordingly. And each cell in this DEM contains only one value representing to the surface elevation within that particular pixel itself. So you can, for example, you can also have a single band orthophoto, which is often referred to as a panchromatic or a grayscale image popularly. Now, most satellite imagery, on the other hand, has multiple bands. So these imageries typically contain values which range, like within a particular range or a band of the electromagnetic spectrum. Uh, when we're talking about these multiple band imageries, each band usually represents a segment of this electromagnetic spectrum, which can be collected using a specific specialized sensor. So bands can represent any portion of the uh, electromagnetic spectrum range, which may not even be visible to the eye, such as infrared or ultraviolet sections, which are very popularly used. This term band, it actually originates from the reference to a color band, because as when we talk about the EMS, the electromagnetic spectrum, we understand that each section of it is divided into an individual band, which may be the color band, generally the RGB within the visible section, and otherwise, if you go further, we have other ranges which are not visible to the human eye. Now, generally, raster bands can range from 3 to 10 as classified in the numerology for these bands, which fall under the category of multispectral. An example of these multispectral images could be the Landsat dataset or Sentinel data. Uh, on the other hand, we also have hyperspectral imagery, or hyperspectral sensors, which actually contain hundreds of bands. So the range of those individual bands is very small in comparison to this. And an example of these sensors can be the GOI, Worldwide View, or sorry, the World View, I'm sorry, and the Iconos or QuickBird. When we're talking about raster analysis, we need to understand that the raster analysis can actually be performed on 4 different levels. So it can either be, or these operations that are actually performed for raster analysis are on 4 different levels. We have the local level, which means pixel by pixel, or we have the focal level, which refers to within a particular boundary of the pixel itself. Then a zonal level, wherein this boundary expands in size, and then obviously the global level, which can be better represented in terms of a very large section across the raster, or even entire globally. So local operations can be performed on single or multiple rasters. And when used on a single raster, or local operation usually takes the form of applying some mathematical transformation to each individual cell of the grid. For example, if we were to say, a researcher may obtain a digital elevation model, and with each cell representing the elevation in the feet, the researcher may need to represent those elevation in meters. which means a simple arithmetic transformation of the original elevation in feet can be multiplied by a value of approximately 0.305, which gives you the new elevation in meters. So this simple arithmetic operation can help accomplish this task. There are obviously other local operation tools also, which can be very popularly used, which is working with multiply, square root, or other mathematical operations. Now, focal or neighborhood operations, these basically produce an output raster dataset in which the value at each cell location is actually calculated as a function of the input value of the cells within a specified neighborhood of that location. So, or that's pixel itself. So each cell is in the input is actually processed, and then the neighborhood is essentially a moving window which shifts along with it. So let's assume if we were to take a particular cell in which in the first row and the first column, excuse me, then corresponding or maybe the second row and second column, corresponding all the cells which fall around it, whether diagonally or directly above or below, left and right, those would form its focal neighborhood. Now, in this case, as each cell is processed individually, and as the window moves or shifts along with it to calculate each raster, the configuration generally tends to remain the same. That means the size of the neighborhood remains the same. So does its shape. And specifically, the value of each cell is dependent upon its direct neighbors only. Now, most typically used neighborhood calculation is a 3 by 3, which means a total set of 9 cells are utilized to calculate the value as represented in the image itself, which is a pure 3 by 3 in this case. Now, zonal operations work on a much larger level compared to the focal or neighborhood operations, where you can compute an output raster data set and the value of each or the output value of each location or each pixel is dependent upon the value of the cell at that particular location and its corresponding association within a cartographic zone. So zonal operations are actually similar to focal operations, except that the definition of the neighborhood in a zonal operation is a configuration of the zones itself. So in case we have a particular boundary that is being worked with, then that is a zonal operation and may not necessarily hold the shape the way it does in neighborhood operations. Now, individual zones can be of any shape or any size and may even be disconnected from each other, which means while in focal or neighborhood analysis, the window keeps on shifting cell by cell, which means row by row and then further column by column. In this case, it may not work like that. And each zone can then be defined as an individual raster or even converted to a feature data set. For raster data, a zone is actually all cells with the same value. So in case we have a particular set of cells with a similar value, it would formulate a particular zone itself. And a zone in terms of a feature data is actually the features with the same attribute values. In case there is a specific attribute value being represented in the raster, if you were to give an example, classification in land use, and we have the land class defined as a particular category of agricultural land or category 4, then accordingly that would formulate a zone. Now, global works when we are talking about per raster itself. So the analysis is not done pixel by pixel or neighborhood or zone wise, but rather for the entire raster, which means the output value at each cell location is potentially a function of all the cells combined from various input raster data sets. So there are basically two main groups which are used for these global operations. It is either weighted distance or we have the Euclidean distance. two main popularly used global raster functions. Now, when we talk about rasters, the first and foremost thing that comes into play is actually creating surfaces. So we can use different interpolation tools to create a continuous surface from discrete samples with measured values such as elevation or maybe chemical concentration and so on. And there are several interpolation tools, as the query was also just brought up, which actually have a variety of parameters to influence the final resulting surface which is being generated. So we, for example, can work with IDW, wherein we can estimate the surface values for each cell using the value and distance of the nearby points. The interpolated values for IDW are a weighted average of the values of a set of nearby points. Weighted so the influence of nearby points is greater than that of a distant point. That means that it works with the inverse of the distance itself. Nearest neighbor or natural neighbors, as it is also known, is interpolation similar to the IDW interpolation, except that the data points used to interpolate the surface values for each cell are identified and then weighted using the Delaunay triangulation. So that Delaunay triangulation works on the same laws of triangulated irregular network. Now, in natural neighbors or nearest neighbor interpolation, reliably works when a much larger data set uh, is used for the interpolation methods. Then like it works on much larger data sets more accurately. Spline is generally used to fit a mathematical surface through the points such that it minimizes the sharp bending. So it is usually useful for surfaces which vary smoothly, such as water table heights or so on. Trend, on the other hand, is good for actually identifying a coarse scale pattern in data, and the interpolated surface rarely passes through the sample input points in this case, because it generally tends to generalize the pattern itself and works on a very coarse scale. Kriging, on the other hand, is a very advanced surface technique, which is most useful when there is spatially correlated distance or directional bias in the data. Now, for creating these surfaces, there are multiple tools which are primarily used in the form of analysis. And these tools are slope, aspect, hillshade, and curvature. The slope tool calculates the maximum rate of change from its cell to its neighbors, which is typically used to indicate the steepness of terrain. The aspect tool calculates the direction in which the plane fitted to the slope faces for each cell. Now, the aspect of a surface typically affects the amount of sunlight it receives, as does the slope. So in northern latitudes, places with a southerly aspect tend to be warmer and drier in comparison to the places which have a northerly aspect. The hillshade function is used to produce a grayscale 3D representation of the terrain surface with the sun's relative position. That means it is dependent upon the azimuth as well as the altitude, and is then these two corresponding values are used for shading the image accordingly. Hill shading is a technique for visualizing the terrain determined by a light source and the slope and aspect of the elevation surface. Curvature calculates the second derivative of the surface, that is whether a given part of the surface is convex or concave. So a convex parts of surfaces, or if I was to give it like an example in terms of geographical features, could be ridges, wherein we have the features generally exposed and they drain into other areas. Concave features, on the other hand, could be an example like channels, which tend to, you know, they're more sheltered and actually accept drainage from convex surfaces. The curvature tool has a couple of other variants also, which is plan and profile curvature, which are primarily used to interpret the effect of terrain on water flow and erosion. So the profile curvature actually affects the acceleration and the deceleration of flow, which influence erosion and deposition. And accordingly, the planiform curvature influences convergence and divergence of flow. Now, when we talk about raster analysis, one thing that can never be skipped is reclassification of the rasters. Uh, when we're talking about this, see, one way to convert surface data into a more usable information for an analysis is to reclassify the surface. So reclassifying a surface sets a range of values equal to a single value. You might reclassify a surface so that the areas with the cell above a given value or between two critical values are given a specific code, and other areas are given another. Or you may use the reclassify or the slice tool to divide a surface up into a given number of classes as a means for aggregating and generalizing detailed data. Reclassifying surfaces is often done to reduce the number of output categories for overlay analysis. Now, besides this, we have certain other tools also, which are actually popularly used. So the weighted overlay or the weighted sum tool allows you to combine multiple rasters of with varying importance. So this is actually useful in terms of when working with site suitability analysis, where several factors contribute to suitability, but only certain factors contribute more heavily than others. Hydrology tools, for example, such as flow direction or flow accumulation, uh, can be used for determining the water accumulation and flow direction or even generating a drainage basin. Accordingly, the spatial analyst extraction tool set, for example, the extract by mask or extract value to points is used to extract vector features out of the raster, or from the raster are actually the surfaces, so that in a way a tabular summary or maybe even smaller raster can be generated from those input samples. Visibility tools are also very popularly used. For example, viewshed or line of sight, which are used to analyze the visibility of parts of surfaces between two locations based upon the observer's point of view and direction of view accordingly. So these are the most popularly used raster analysis functionalities that are available. Let me just give you or lead you into a small demo for raster analysis. We'll first talk about working with NDVI raster function. So we'll look into that. In this demo, we will use the ArcGIS Pro platform to see how to work with raster functions. Raster functions create on the fly layers, and you do not really need to save them anywhere. We have Landsat 8 imagery, which is being utilized for a location somewhere near Shimla. Now we will generate a normalized difference vegetation index, which is an NDVI imagery using Landsat imagery here. NDVI is generally calculated by using NIR minus red divided by NIR, which is near infrared, plus the red band combination. And NDVI highlights our vegetation areas. So once we've actually executed that function, to execute that function, what we will do is we will actually click on the imagery tab, and on the title bar top pane, and click on raster functions. Having accessed the raster functions, we can search for and open NDVI in the raster functions. And once we've done that, we will take the Landsat imagery as input here, as taken earlier. And once the corresponding Landsat imagery has been provided as input, you will provide the band of the corresponding visible band and band number of the visible band and the near infrared band. And accordingly, the function will then analyze the output. The scientific output option can then be must also be checked to, and then click on create new layer to finally give you the required output. Now we can see here, if you look at the NDVI which has been computed, is that the vegetation values which are above approximately, if we click on the map and identify the dark regions. So the vegetation values which are above 0.3 actually are the yellow or dark regions. And land snow is represented in the violet or dark blue negative values. So we can then use the remap or remap tool to actually classify these values to differentiate between no vegetation, shrubs, moderate, and high vegetation areas. But instead of doing that, let's create a custom raster function that will actually generate an NDVI and remap it also for us. So obviously we can use it manually, but if we try and create a function, we can automate the process. So we'll go to the function editor in the imagery tabs. We'll search for NDVI and drag it onto the editor. We'll do the same for remap. We'll connect NDVI to remap by clicking on the NDVI function and dragging an arrow to the remap. Having done that, we can then right click on the NDVI function and select visible band 4 and infrared band ID 5. We'll check the scientific output. Now we'll go to the variables tab as visible and check is public for the first 3 rows and click on OK. We'll right click on the remap, which gives us the range of -1 to 0, and output can be between 0 and 0 to 0.3. Output 1 will be 0.3 to 0.5, and output 2 we can classify between the range of 0.5 and 1.
Quick time check, Sarthak. We have about 5 minutes left.
Yes, Dhanraj, we're trying to wrap it up quickly. I guess all I'll need is approximately 5 to 7 minutes beyond this. Once we've done this, we can simply click on OK after we've given the node data values, and we'll click on save and give the name and description accordingly as required. So we can save this particular function, provide its corresponding attributes, and save it. Now to access this function, we can go to the custom tab in the raster functions, click on the function that is just being created, and take Landsat as input raster, and we can change the other values if needed, whichever are required within the particular remap section. Having done that, once we click on yes, it will give us the particular output which is required. You can see that the output raster has values ranging from 0 to 3. So we can click on the color ramp to change the symbology and change the primary symbology to unique values. Now, having done that, we can also provide descriptions accordingly for each individual unique value. As we had discussed earlier, which is the final requirement to give us to change the symbology. So you can keep, you can identify that as we're changing the values here in the symbology pane. Corresponding to that, the values within the table of content are also updated. the key point of actually understanding the correct symbology for this is having a detailed understanding of the entire workflow, which needs to be set for output. Once we have done that, we can utilize this to identify areas of no vegetation or low vegetation, moderate and high accordingly. We also have a small demo for terrain analysis. So we'll all talk about terrain analysis also here. In this demo, we will use the ArcGIS Pro platform to create a slope, aspect, and hillshade from the DEM which is available on the map. So we have a DEM again near the location of Shimla, and we can visualize the DEM in the 3D section within Pro itself. To calculate the slope, we'll go into the analysis pane and open tools to open geoprocessing pane. If not open already, search for slope and open the tool. We'll take the DEM as input raster, and you can change the Z factor and if X and Y are Z in different units, or keep it default for now and run the tool. Once the tool is executed, we can click on the symbols under the slope layer to change symbology. So we will change the method here to geometric interval and color scheme spectrum by wavelength bright. You can see areas with steep slope in orange or red and gentle slope in blue accordingly. So as the symbology is updated. You can see that it is still processing here on the window. Once it is successfully processed, the output will be visible as shown on the map. Rendering does take time at times if we are working with a large data set. But once the corresponding renderer has completed its execution, accordingly the output is obtained. You can also see how each pixel is individually classified based upon the values which are represented here for this slope angles. Now further, our next step is to work with aspect. So we'll search for aspect in the geoprocessing pane and open the tool. We'll take the DEM as input raster and run the tool. The remaining parameters we can leave as default for method. Once we have executed the tool, the output will be visible on the map itself. You can see that the direction that the slopes are facing is accordingly represented in the symbology. So north-facing slopes are in red, and similarly, south-facing slopes are in cyan, and further color scheme has been followed. So that can be used for better representation of the aspect of the terrain itself. Now, the final one that we have is hillshade. For this, we will open the hillshade tool from the geoprocessing tool, geoprocessing pane. We'll take the DEM as input raster. We'll take the default azimuth and altitude as 315 and 45. That is the position of the sun is at northwest. Now you can change that as per requirement, and you can also update the Z factor if required. If X, Y, and Z are in different units, and accordingly run the tool. The final output, which is represented onto the map, the renderer seems to be taking some time, will give us a grayscale image wherein we will be able to identify the correct hillshade. So within the visible section that is being rendered here, you can see that the bright and dark areas in this image represent areas which, as per the position of the sun, which we had provided as input. So all of these rasters which we have just generated can be used for solar farm planning or flood modeling, urban planning, erosion modeling, and similar other workflows, so as to generate the corresponding output. Now, this concludes our trainings for the day. We have discussed all the material. In case we have any queries, we can definitely take that up quickly, although we are a little overshot in terms of time. I will also like to refer all of you to the following URLs to study more about the details available within ArcGIS Pro, as well as certain essentials of geographic information systems. If you have any queries, we can maybe give a couple of minutes to take that up accordingly.
Hi, Saptak. It's not related to what we had presentation. So actually, I have, let's say, 100 buffers, and I have like 5 crop types, and I want to calculate each of the buffers, like crop types. So, is there a tool which I can use so that I can have like a separate column for each of the crop types represent with showing their area in one shot, or like, yeah.
So the requirement that you have, sir, we do not really have a corresponding tool for that, which can actually, take 5 different attribute values and help you classify 5 different columns based upon the agriculture classification that you're talking about, for instance, or the land value classifications. The best way to build this will be to actually build a geoprocessing model, wherein each particular section appends a new field and calculates the value based upon intersection. So this can actually only be achieved using a geoprocessing model, or a geoprocessing script or a custom tool, which can be built with relative ease, because there is corresponding documentation also available for the same. However, there is no direct tool which can actually help you satisfy this requirement.
Okay. Okay. Thanks, Satak.
Hello.
Right, so do we have any other queries?
Sarthak, Sonali here. Can I ask one query?
Yes, ma'am, please.
Yeah, first of all, it was a very good presentation. And I have not used ArcGIS much, so this was like kind of an introductory session to me. So I just wanted to know, is Python or R anyway related to this, for further learning of ArcGIS or putting it to use?
So let me just reframe your question for you, ma'am. In case you're talking about understanding how to work with ArcGIS, from a more analysis level perspective, definitely you do not need an understanding of Python or R or any such language. But if you are talking about trying to automate certain analysis workflows, as Mr. Narang just brought up, so then in that case, definitely having an understanding of Python, having an understanding of R, being able to build the computational statistical models for using R in ArcGIS Pro, and custom tools, so as, for example, to satisfy the requirement that Mr. Narang has. In this cases, to answer more complex or to build more complex solutions, definitely having an understanding of Python or R helps. But if you're talking about having a more streamlined flow without any customizations and advanced solutions being built, then in that case, you can simply, there is actually a wide range of tools also available. So you can work with those and still manage to have a good grasp over spatial analysis.
Okay, okay, understood. Understood. Yeah, thank you so much.
You're welcome, ma'am. So I think we have overshot our allocated time period here. So I'd like to hand over the session back to Dhanraj for closing.
Thanks, Arthur. Thanks. Yeah, I think I'll keep it really short. Glad that all of you could join. I think we had some fairly good questions coming in. Sarthak, thanks for taking them. I've just shared the link to all the previous sessions in the chat box, and we will be sharing the recording for this session as well. Beyond this, if there's anything else that, if there are any other questions, guys, you can please feel free to unmute yourself. We can maybe take one or two questions quickly if you still have any. Otherwise, always available at developer@esri.in. I'll just put it down again in the chat box, and you can write to us with your queries regarding this session or anything else at all. And we'll be sure to have them addressed.
Yeah, I can ask one more question if it
Sure.
is the time.
Sure, Aditya.
Thanks, Anurag. When you referred Sarthak geoprocessing model, yes, I am like I have not worked with R, like because we have one package in which I can use like give the commands and I can get the outputs using R. So when you refer to geoprocessing models, so in that case I can also use those tools in R and I don't require any credits to do so. Is it like that? Can I assume like that?
Yes. That is absolutely correct, Mr. Naran. You do not really need to work with, like you do not really need any specific credits. If you have access to ArcGIS Pro, you have the corresponding licensing also, which is required. Then you can definitely build statistical analysis models using R. But this is only specific to ArcGIS Pro. So in case you're working with ArcGIS Desktop, which means ArcMap, then in that case, we do not have R embedded.
Yeah.
Additionally, so that is
Yeah.
one key point there. ArcGIS Pro is the key point here. And when we're talking about the geoprocessing models, yes, by default, almost everything or all geoprocessing within the ArcGIS environment, when we're talking about ArcGIS Desktop or ArcGIS Pro, is dependent upon geoprocessing and which is corresponding to Python. So these two things go hand in hand, and you do not really need any specific kind of credits as such, besides the basic license that you have available.
All right. Yeah. Thanks a lot. Yes, I was just curious if I need, because I don't have the credits, but I have the license for ArcGIS Pro and ArcMap.
Then you're good to go. So you can work with all of this without any issue.
Thanks, guys. It was very insightful, as I said. Yeah.
Thanks again. Thanks, Sarthak, for taking the questions once again. Thank you all for joining, first of all, this rescheduled session and being very active and very vocal with your doubts. Like I said, we'll be sending you the recording. And thanks for just being constantly available for these webinar series. It brings us to an end to the 6-part series. And we'll share any useful links with you over email. We'll also be hosting all these sessions on our website. So would love for you guys to refer to those links and pages. Thanks once again, and have a great weekend ahead.